126 students, class 12 syllabus on full swing, and we are on the lecture number 3 of magnetic effects, magnetic sources. And today we're going to see how magnetic field can apply a force on a current carrying wire, and also when you convert that wire into a loop, it creates something called as a magnetic moment, and it can experience a torque and all of that. So all of this in today's session with me, your Captain Shreyas, on the number one J English channel of the country. Yes, Vedantu J English. Hi, Wu. Hi, GM. Welcome. Uh, Abhi, Harshita, everybody aboard. And I hope you guys have registered for the Vedantu's Mega Scholarship Admission Test. Yes, it is. Open the registrations. The test is on 4th October, 5th October, 11th, and 12th October. You might be like, sir, this is August, September, what? Lot of time. Let me tell you, students, take this test very seriously, and you can guess that by the number of test takers itself. 2.5 lakh test takers last year, and this year too expected that much or more. And there are amazing gift prizes, cash benefits, everything. 2 crore worth of just cash prizes, and lot of gift hampers for all of you. And there is a scholarship pool in case you are interested to take admission in Vedantu. Even then, if you are not interested to take admission, still you are getting gifts. You are getting to compete with kids, and you get to know where you stand, and a beautiful report card which tests all your thinking capabilities, cognitive abilities, everything, and gives you a beautiful analysis. So make sure you're writing it, and also a lot of goodies to be won. And when you go to the center and write, you get to meet us. Yep, I will be also there in many centers. You will be also meeting a lot of teachers. So make sure you are registering for the Vedantu's Mega Scholarship Admission Test. Okay, the link is there in the description box of this video. First of all, like the video, guys, in case you have not liked it yet. Okay, and down if you go, you will see the link over here, MVSAT, register now. Okay, this will open it up. Enter your details. Sir, my city is not there. Don't worry. Register now. If we see a lot of registrations, then we'll also conduct the test online. But register right away, right now. That is very important. Okay? Yes, hello. Tilak, hi, Hansika. We can apply through the link in the description box. Can you see the description box? There is a link over here. Just use that link. Okay? Fine. Welcome, everyone. Hi, Sashwat. Welcome, Hansika, everyone. Can I apply in 9th class? Yes, my dear. This is for all the kids. This is for, see, IITJEE, NEET, school board, whatever, grade 7th, 8th, 9th, 10th, 11th, 12th, and dropper, all the students. So for 8th standard, the test will be separate. Don't worry, you will not be given high level stuff. 9th standard, the test is separate. 10th separate, 11th separate, 12th separate, dropper separate. So every grade has a different test. That is why you need to select your grade. Okay, right. Oh, right. Yes, Ibu, why not? I will definitely address your doubt. Please mention it in the chats. Okay. Now, let's talk about magnetic forces on a current carrying wire. We know that a moving charge, a moving charge in magnetic field, experiences Lorentz force, which we talked about. Lorentz force, which we talked about in the previous lecture. So if you have a charge which is moving and there is some magnetic field, then there is a force which acts on it, QV cross B. So maybe like this. So this is that force, which is nothing but Q into V cross magnetic field. Now, if that is the case, imagine there is a current carrying wire. Okay, this is our wire, which is, let's say, carrying current. Okay, this is carrying some kind of current like this. If the current is moving inside the wire, it is as good as saying there are some charges in motion. There are some charges in motion, although the positive charges don't move. Basically, the nucleus doesn't move. The electrons go this way. It's effectively saying these positive charges are going like this. Effectively, not actually. Actually, negative charges move. So keep that in mind. So it's as good as saying there is effective positive charge going in the direction of current. So therefore, in a current carrying wire, in a current carrying wire, in a current carrying wire, we see there are moving charges. There are moving charges. There are moving charges. And the moment you have moving charges, we know they experience force. So, if there is some kind of magnetic field in this particular region, imagine there is some kind of magnetic field. Now, under the influence of magnetic field, under the influence, under the influence of magnetic field, what will happen? Yes, that same wire will experience a force. The wire will experience a force. This is the logic behind it. Because the current carrying wire has moving charges and moving charges does experience a force. So current carrying wire will also experience a magnetic force on it. Is the logic behind it clear? We'll see the formula also. Okay, right. Azad will make a separate video if you want. Okay, right. All right. Okay. Hello, Samiksha. Yesterday, when I was charging my device, the charger was coiled up like a solenoid and it started vigorously vibrating to and fro without any external contact. Why did it oscillate so vigorously? Oh, maybe possible that who was asking that? Ibu. Yes, maybe it was possible that there was some magnetic device around it. Maybe the phone itself is magnetic in nature. The solenoid is created, which is obviously again magnetic in nature, and the AC current which is passing through it is alternating. The magnetic field is reversing. So quite possible the magnetic field reversing caused that kind of vibration. Is that okay? Most likely that would have been the reason for that. Yeah. Or maybe some metallic thing would have been there. Yeah. All right. Oh, you failed in the AC test, then wait for me to start the chapter or watch my older classes, which is there in the playlist. Okay, road series or anything else. Okay. Now, we'll see what is the formula for that. The formula for that goes as follows. If you have a element of wire, okay, let's say that element is having a length of dl and the current which is flowing in it is I, then I can show dl as the element of current wire or element of the wire carrying current. It's a part of a bigger wire. Please remember that. Yeah, that wire is actually huge. You're just taking a small part of it, just like we did it in Biot-Savart's law. Okay, so this is just a small part of that big wire. Okay, that big wire is somewhere here. Then, if there is a magnetic field like this, then the force which acts on it, is going to be dF. This is the elemental force. Because you are taking a small element. That will be equal to, you take, instead of charge, you take current. Instead of velocity, you take dl vector and then do the cross product with the magnetic field, I dl cross B. This is the formula for finding the force on that current carrying element. So here, the element is like this, magnetic field is here. Using the right hand thumb rule, L cross B, it will go like that maybe. So Chuma, I'm just taking some random things over here. So the force might probably be like this. The force might probably be like this. This is the force. I L cross B. If you do, L is there, length is along the current, magnetic field. So maybe it will be in that particular direction in 3 dimensions. Now, a lot of people try to use Fleming's left hand rule, right hand rule, uh, Fleming's toe rule, Fleming's right foot rule, and what is this? This is I, this is L, this is B. Then the examiner is thinking, what happened? Why are you pointing fingers? And you will get disqualified. So, my dear students, please don't use all these stupid rules. It's a waste because you will first of all not remember it. Beautifully, you will write the diagram ILB. Oh, sir, in EMI, this is the right rule, sir. You will unnecessarily figure out some nonsensical thing and you will get confused. So better to always use cross product because cross product, always works with the right hand. There is no confusion. If you know I, L cross B, that's it. You will do L cross B. Whatever is the thumb, that is the direction of the force. So you don't break your head over it. Okay. Samiksha, the classes are of 12th standard at 8 o'clock. Okay. Hi, Pritija. Welcome. Hi, Amla. And 6 o'clock, you have the 11th standard. Yes, Azad, I will definitely do a video. All right. So without any rules, how to find magnetic field? Magnetic field will be given to you. How can you find force without magnetic field? So without field, you can't find force. So this will be given, this will be given, direction at least magnitude. From that, you can find force. Okay. So length cross B. As you can see again over here, if for example, my DL vector is over here and this is some plane, hypothetical plane, and let's say my magnetic field is over here. Then there is some nice angle between the two. Well, looks like the Indian flag out here. And let's say this is theta. Then the force will be perpendicular to that plane. So this is how your DF vector will be. It will be perpendicular to B also. It will be perpendicular to DL also. Okay, that is how it will look. Magnitude wise, it will be IDLB sine theta. So if you ask me the magnitude of DF, obviously it will be I into DL into sine of theta into basically B. That cross will be replaced by sine theta because it's a cross product. Sir, but I want to figure out what is the net force on the entire wire. So maybe that wire is from here to here. Okay, this is that entire wire which is there from point A to point B. Then if I want to figure out what is the net force on the entire wire, that force will be addition of this df. Addition means integration from point A to point B. That's it. So basically our net force will be integral from point A to point B df, which is nothing but your I into dl cross producted with your magnetic field. With your magnetic field. That's it. Okay. So this is what you will do. Basic integration, because you have to add all the forces. Every point will have some df force. So maybe some df force here, some df force here, maybe df force here, maybe like this, like this, like this, like this. All these forces together, you add them, you will get the net force. Got my point? Everybody clear? Give me a thumbs up, smash the like button in case you have forgotten. Okay. There is no old videos of Sigma on YouTube. You will find it in the past sessions. Just give it one more day because 20th, I think the batch is starting. So tomorrow onwards, you will start seeing the older videos. The batch starts tomorrow, right? Every access will start from tomorrow, 20th or 21st, if I'm not wrong. Okay. Oh, right. Shreyas, I'll probably reply to you later on. I will break the flow otherwise, right? Or else everybody will start asking doubts. Okay. Hi, Sanju. All right. Amala, clear. Perfect. Okay. Now. Yes, don't use any Fleming's rules now. Now that you understand, okay, sir, this is how the force is. Imagine I tell you there is a wire, conducting wire like this. Imagine I tell you there is a there is a um, there is a uh, conducting axle of a train whose length is 2 meters and 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 the magnetic field of earth is vertically down of value 2 into 10 to the power minus 4 Tesla. If a current of 5 amperes is passed, how much force will it experience? How much force will it experience? Very interesting question. Let's try to solve this. So let's visualize it from the top. Okay, imagine this is the rails and these are those axles like this. Okay, like that. And imagine any one such axle right now. Say, for example, I imagine this particular axle right over here. Okay, this particular axle right over here. And the wheels are over here like this, like this, like this. These are the rails, right? Imagine you are seeing the top view. The length is given, and the length is how much? It is basically 2 meters. The current is also given through that axle, which is basically 5 amperes. And magnetic field is going through it. Let's say the magnetic field is vertical. It's clearly mentioned. And since you are seeing the top view, the magnetic field lines will look like a cross or a dot. Anyone. So the magnetic field is given 2 into 10 to the power minus 4 Tesla. That is also mentioned. So if this scenario is there, clearly there will be a magnetic force on that axle. How? In the scenario shown, if I do IL cross B, length is up, magnetic field is inside, length cross B will go here. Length cross B will obviously go here. So there will be a force in this direction. There will be a force in this direction. So it's crazy to think I can make a train move by this force. I'm saying crazy because I feel the force will not be enough. But yeah, it's a very interesting idea though. Imagine you are using Earth's magnetism, you are passing current in the axle, no motor, and the entire train begins to move. Unfortunately, Earth's magnetic field is not very strong. But if Earth was like a neutron star, some crazy planet with some crazy magnetic field, if you pass current, even small amount in the axle, that force will be good enough to start moving the train. You reverse the direction, the force will be reversed. Isn't it crazy to think about it? Yeah. Yes, correct, Ibu. Fleming's rules are basically trash. All right. The class timings for Sigma batch are in the evening, around 3 o'clock to 8 o'clock, 9 o'clock. Yeah, usually that time. Okay. Few classes are there in the afternoon, but that is 3 o'clock, but not every single time. Most of the classes are in the evening time only. Yeah. So how much will this force be? Magnitude wise, it will be current into length into sine theta instead of cross, because magnitude I'm interested in. Okay, current is how much? 5 amperes. Length is how much? 2 meters. Sine theta, angle between the length and the magnetic field is 90. So sine 90, okay, into magnetic field, which is 2 into 10 to the power minus 4. 5 2s are 10. Sine 90 is 1 into 2 into 10 to the power minus 4. So this will become 2 into 10 to the power minus 3 Newton. So this is very small force. Obviously, it will not be enough. Getting my point, everyone? All right. Okay. Okay. I'm not sure what Tamil channel has told or anything, my dear. But all the classes over here have the recordings. I'm not sure what you are saying. Just go to the channel. You can see beautiful playlists are there. Yeah. See, this is the last year's Roar series. Entire syllabus is there over here. If you go to playlist section, you can search for Pathfinder and Nurture playlists that also has extensive syllabus coverage. Okay, you can see Zero to Hero series also, and the current series also is continuing over here. As you can see on the home page, for class 12th and class 11 separately, we have created the playlist. It's all there over here only. You don't have to go anywhere else. Yeah, fair enough. Now, let's go to the next kind of question over here. Let's see the next question. Here we have Here we have basically two rails like this, and they are connected by a battery with some internal resistance. Let's say the internal resistance is 2 ohm, the battery voltage is 10 volts. There is a conducting rod which can slide freely on it. There is a conducting rod which can slide freely on it. The length of the conducting rod, basically, let's say it is given to be 4 meters, 4 meters, and the rod itself has a resistance of maybe some 3 ohms. The rod itself has a resistance of 3 ohms, and there is a mass of the rod also. Let's say it is 0.1 kg. Let's say it is 100 grams or 0.1 kg. That is also given to me. Now, all this is from the top view. What we see is basically, uh, you know, uh, the magnetic field lines going inside like this everywhere. The magnetic field lines are going inside like this everywhere. And let's say that is also magnetic field is also given to me. And let's say it is 10 to the power minus 2 Tesla. 10 to the power minus 2 Tesla. That is also given to me. Interesting. Now, the question is, in this particular situation, if the rod starts from rest, okay, can you find the acceleration of the rod in general? Can you find the acceleration of the rod? Okay, that's the question. Okay, just when released. Find the acceleration of the rod when it is released. When it is basically released. Beautiful question. Let's see how do we do it. Again over here, as you can see, there is a closed circuit which is formed and in which current will begin to flow. How? This battery will supply some current. It will go like this. It can go there, but it is endless, so it can't complete the circuit. It will go like this, it will go like this, and this is how it will go. So there will be some current in the circuit. That current will be in this particular manner. So there is a closed circuit formed. Can we find that current? Yes, it is basically the total EMF upon basically the total resistance. So in this particular circuit, the EMF is only one, which is 10 volts. There is one internal and the rod's resistance, which is 3 ohms. So 2 plus 3, so which is 5. So 10 by 5, which means 2 amperes of current will go in that circuit. Once the current begins to flow, because there is magnetic field, there will be a magnetic force. How will that force be? Well, the length of the conductor is along this particular way. So this is how the length is. The magnetic field is inside in this particular manner. So if you do L cross B, take the fingers of your right hand, point it down and slowly bend it inside. You will see the thumb pointing towards your right hand side. So this is how your force vector will be using right hand thumb rule. Simple. So there will be definitely a force acting on the rod which will cause acceleration of the rod. So can we find that force? Why not? Force will be I into L into sine theta into B. Current is just found out 2 amperes. Length is 4 meters. Sine of 90. Why 90? Because length and magnetic field length is down like this, magnetic field is inside, they both are perpendicular to each other. So sine 90, magnetic field is 10 to the power negative 2 Tesla. So 2 fours are 8 into 10 to the power minus 2 Newton. That is the force. But that is not the only thing. You have to find acceleration. So acceleration will be force by mass by Newton's law. This is using Newton's law of motion. So therefore, 8 into 10 to the power minus 2 divided by 0.1, which will make it 8 into 10 to the power. 0.1 goes on the top as how much? 10, right? So this will become 10 to the power minus 1, which is 0.8 meters per second square. That is the acceleration. That is the acceleration. Got it? Very good, the creator Kora. Perfecto. Pritija, do you follow that rule? Which rule, Pritija? I'm not really sure. Sir, in road series, some videos are missing the playlist, but it's published in the video panel. Kindly check. Okay, maybe they were not added to the playlist. I will definitely check that, Ibu. Thank you for pointing it out. But I think if you just search on YouTube, normal search bar, you will anyways get it, right? That is how it works. Okay, now let's see the next part on this. Let's see the next part on it. Imagine, imagine, imagine the wire is curved and now you want to find the magnetic force. So you'll be like, yes, sir, you just told about it. If the wire is curved or anything, then you have to integrate. I don't like integration, man. Like, why unnecessarily waste of time, right? So here is a very nice trick for it. So whenever you have some wire which is curved, okay, let's say this is a wire which is curved in nature like this. This is a curved wire and there is some current which is flowing through it and you have to find the force on it. So the force due to the magnetic field on a curved wire, you want to figure it out. What you do is, ideally you would have to integrate and go like this, right, from A to B, but you can avoid this integration. So you can completely avoid this particular integration and instead what you can say is just draw a wire from the starting point to the ending point. Just draw a wire, imaginary wire. This will be the imaginary length. I will call it the effective length. This is the effective length. Now imagine a wire of that same effective length carrying that same original current. That same original current. Whatever magnetic field was there before, that same magnetic field is there now also. So if you do IL cross B, let's say this was the force, this is the force, you will get exactly the same force as that on the curved wire. So instead of doing this integration, just say we will find the force on the effective wire and my job is done. On the effective wire, straight wire joining the ends and my job is done. So force on the straight wire means you take the same original current, you take the effective length and cross product it with our magnetic field. So that is the force on a curved wire. It's like displacement, guys. Just joining the initial point and the final point, you're getting the answer. Okay, so very, very important rule for solving many, many questions. Yeah, awesome. Jaswant, I think few months back you had asked, can I crack JEE in 6 months or 5 months? Is that tomorrow Sigma Express, Sigma 2 have same class? Yes, Anubrala, because whatever classes you have missed, you will be getting it live as one shot live, and whatever you miss, you also get the recorded versions of that, so that way you're not missing anything live, plus you are able to cover your backlogs on time if you just follow the flow of the class. And I'll be conducting a special entry point class for all of you to guide you, mentor you, and tell you how to use the batch properly, explain you all the features, everything. Okay, there will be an orientation also separately, okay, in Sigma Express, right? Okay. Pritija, I don't know about other channels, but here we send the PDF and we also record the video. So I mean, always all our videos are there. Just check, no, my dear. Like, why are you asking these questions? It's there, no, here only. See, just open up any thing over here. You will see all the videos are there. Nothing is getting deleted or nothing is, removed or anything. If you open any particular video also, let's say for example, I open this particular video, you will find the PDF also. It is there here only. Yeah, PDF is there. See, PDF is there. Everything is there. Okay. So you can just see, no, rather than asking. All right. Now, now over here, observe this carefully. Observe this carefully. If I take complete loop, if I take a complete loop, meaning the wire starts and ends at the same point. This is a loop of a wire. The current is just circulating inside of it. Okay, the current is just circulating inside of it. What do you think the effective length will be? What do you think the effective length will be? Yes, it will be a big fat zero because you're starting and ending at the same point. So therefore, you will see that the force on a current carrying loop will always be a big fat zero. Very, very important. Okay. The force on a current carrying loop will always be zero. Yeah, because the effective length will be, yes, correct. Hereafter also you will be getting the PDF, lectures, everything. Why will we delete? Will not delete anything, man. Don't worry. Now there is one small condition when you apply this. The small condition is the magnetic field should be uniform. So this only works when, when, when magnetic field is uniform. Okay, magnetic field is uniform. Same thing here also. The condition is when B is constant. B should be constant. If one place it is strong, weak, it will not work this formula. Then you have no other option but to integrate it. Let me show you live example of, this particular formula. Say for example, we take a wire which is semicircular in nature carrying some current I, and let's say the radius is R, and let's say the magnetic field is going down like this. Magnetic field is going down like this over here. Can you figure out what is the force on the semicircular loop, on the semicircular arc, I would say, not loop, semicircular arc? We can definitely do that. Whenever you have a curved wire, you can replace it with a straight wire connecting the ends. So from one end to the other end, if you connect, this will be that wire carrying that same current. This will now be the diameter. So if you ask me what is the effective length, it is the diameter. Diameter means 2 times the radius. So if you ask me now what is the force? Well, see guys, magnetic field is this way. Length is like that. Magnetic field is here. So force will be inwards. Yeah, force will be inwards as you can see over here, because length is like that. Magnetic field is down. Length cross B, the force will go inside. So the magnitude of that force will be I L effective sine 90 into B. L effective is nothing but 2R. So I2RB or 2IRB, that is the force on that semicircular wire. That is the force on the semicircular wire. Is that absolutely clear, everyone? Okay. If you are already in Sigma 2.0, don't join any other batch. It's just continued. Okay, just continue with the same batch. Whatever you have missed, just watch the replay later on, and we will also conduct live one-shot revision in the Sigma batch. Don't worry about it. Okay. Awesome. Yes, Naresh. Yeah, right hand rule we have used for finding the direction. Don't use Fleming's rule and all of that. That is all random nonsense. Unnecessarily, it will confuse you. Okay. Now, just imagine you have two wires placed beside each other, and now we are being asked what is the force between them. Imagine there is a wire like this over here and another wire like this over here. Okay. And let's say This wire is carrying some current, let's say I1, and this wire is current is I2. Will there be a force between them? You might start wondering, why will they start attracting or repelling or any force be there between them? Then you should think, oh, whenever we have a wire, it produces a magnetic field around it. Oh, yes, correct. So this wire carrying current, if I hold my thumb in the direction of the current, my fingers are curling like this. See, it is wrapping like this, right? So there is definitely magnetic field around this. So on this side, the magnetic field comes towards me, and on this side, it is going inside. So there is magnetic field which is going inside like this because of this wire. So that magnetic field will definitely be there over here. Let's say I call it B1, and maybe the distance between the two wires, let's say I call it D. So the magnetic field at a distance D from the wire, what's the formula? Mu naught current divided by 2 pi R. R over here is D. For a long infinite wire, the magnetic field at some distance is mu naught current by 2 pi into distance. Now, this magnetic field on this wire will apply a magnetic force. Use IL cross B rule. So, as you can see over here, length is upwards, magnetic field is inside, magnetic field is inside, length is up, magnetic field is inside. See where the thumb is going? It is going towards the left. So the force will be towards your left hand side. The force will be on this wire, will be on the left hand side. Can we figure out that force? Why not? That force will be current, which is I2, into the length of that wire. I don't know how much length. I'll just assume it as L, into the magnetic field, which is B1. But B1 value already I know, mu naught I1 by 2 pi D. Okay. Rest of the things are as it is, I2 into L, and this is your force. If I bring the length term below, it will become force per unit length. And on this side, we will have mu naught I1, I1 and I2 divided by 2 pi D. This is a very important formula for force per unit length between two wires. This is the force per unit length. Force per unit length between two parallel wires connect, around each other. So this wire will apply this force. If you do the exact opposite, you will see that there will be a force like this on this wire, which will be exactly equal and opposite. Newton's third law. Okay, by Newton's third law, this is how the forces will be. Now, sir, will they always attract each other? The answer to that is no. See, if, for example, you have a wire here where the directions are same versus directions are opposite, when the directions are same, they will always attract. But when the directions are opposite, then you will see that they will end up repelling each other. Same current, same direction of current actually, or I will say parallel current, parallel direction of current. Here it is anti-parallel direction of current, anti-parallel currents. Then you will see that they will repel. It's opposite of electricity. Same charges will repel, right? Here in magnetism, same currents will attract. In electricity, opposite charges will attract. Here in magnetism, opposite currents will repel. So that is an easy way to remember. Magnetism and electricity go opposite to each other. Okay. Kumakula, very soon. Very soon. Surprise is coming. Don't worry. Okay. Yeah. Stay tuned on the channel. Very good, Hasvita. Understood? Clear? Yes, you can take a fresh start from tomorrow, Anburaja, because there will be a fresh orientation. You can as if assume that you are starting fresh, but don't leave that batch. Don't join any new batch. Don't waste your money. Just continue in the Sigma 2.0. Okay? Perfecto. Amazing. Let's go. Now, just take this particular example where you have a long wire carrying current. Let's say that current is capital I, and beside it we have a loop which goes like this. And let's say the distances are also given to me. Let's say this distance is example A, and the length of this is, let's say, 3A. This is 2A, and there is a current which goes like this, which is small I. Okay, there is a current which goes in this loop. Can you figure out the force on the loop? Can you find the force on the loop? That is the question. Can you figure out what is the force acting on the loop? Now you'll be like, sir, force on the loop? I mean, isn't it obvious? Isn't it zero? Because you just told it sometime back right over here. Whenever you take a loop of current, the net force is zero. But that is exactly the question. There must be some reason why that question is asked. And that catch lies over here. That answer is zero only if magnetic field is constant. Yeah. Magnetic field is constant. I mentioned that condition. These theorems, these properties were only valid when magnetic field is constant. Only then you can skip this integration and use the effective length concept. You'll be like, okay, so what? Isn't magnetic field constant here? Think again. This wire is creating its own magnetic field. It is creating its own magnetic field, right? It's creating its own magnetic field. When you are closer to the wire, think logically, the field will be very, very strong. The field lines will be closer to each other, they will be strong. As you go here, the field will slowly become weak, and over here, it will become even weaker. So the field is very strong here versus weak here. That means it is a non-uniform field, non-uniform magnetic field. Oh, so therefore the force may not be zero then. Got my point? Understood? Awesome, awesome. And next week they'll start 12th portion for 3 days, 3 days 11 portion. Yes, you can continue with the same speed or just follow the plan which I have given on the channel, the strategy I have given. Better to go with the school flow so you will not find it weird, or a coaching flow. Follow one flow. Don't get confused. If you are following school flow, then follow school flow. If you are following JEE flow in your coaching or YouTube, follow that same flow. Then don't bother about what is happening in school and coaching and etc. But you have to stick to one thing. If you do this also, that also, it will not happen. Okay. So now what do we do? Other two might help them reducing distance. That is irrelevant. Let's assume the loop is rigid. It will not bend like that because of its own current. That can also happen, but let's assume it's a rigid loop for now. So let's think what about the directions of forces. Okay, one by one. If you ask me one by one, let's see, concentrate properly, guys, on this particular loop. Okay, over here. See, magnetic field is always inside, everywhere. Current direction like this, like this, like this, and like this. Let's use IL cross B. IL cross B. Length is up, magnetic field is inside. Length cross B. My thumb goes left side, so the force is here. This is force on the first side. Length is here, magnetic field is inside. L cross B, thumb goes up. Once you know the thumb is pointing outwards, on every side it will be outwards. Even if you don't use the rule, you will still get it. Here length is down, magnetic field is inside, very difficult to twist, but you will see that the force will come here. This will be, let's say, F2, this will be F3, and here the force will come like this. The force will come like this. Every single place. If this arrow was inside, this will be inside, this will be inside, this will be inside. If this is outside, this will be outside. That is easy way. Don't waste your time in the exam. So that's a small trick. Okay. Sir, what now? What to do now? Think logically whether F1, F3 will cancel, F2, F4 will cancel. Answer in the chat box. Which of them might cancel? What do you think out of these forces? I mean, if you Again, observe carefully. The field is quite strong over here. The field is very weak over here, as you can see. Okay. Here it was still medium. Here it is very, very strong. Okay. And then it becomes very weak over here. Correct. So F1 will be very strong. F3 will be very small. As you can see, this will be smaller force because field is small. Here field is strong. So this will be stronger force or bigger force. But throughout this, same variation happens here also and here also. So F2 and F4 will be equal in magnitude. F2's magnitude and F4's magnitude will definitely be equal. So definitely they will cancel out each other. Therefore, the net force in the y direction will not be there only. So there is no force in the y direction. Clear? Understood? But F1 and F3, they are different. So how much is the distance? First, let's find out from this wire, because we know what is the force acting per unit length formula. We just saw this. The force acting per unit length is mu naught I1 I2 by 2 pi d. Okay, so let's use that formula over here also. So we know force acting per unit length is mu naught I1 I2 by 2 pi into d. So if you talk about F1 first, this wire and this wire, the distance is just A. So this magnitude will be mu naught I1 I2 by 2 pi A. If you ask me this force, it is at a distance of A plus 3A, which is 4A. Agree? The distance between this wire and this wire, this distance is going to be 4 times of A. So this F3 will be mu naught current 1, current 2, II by 2 pi 4A. Perfect. This is strong, this is weak in x direction. So what will be the net force in the x direction? Big force minus small force, F1 minus F3. So that will be nothing but mu naught II by 2 pi common, mu naught II by 2 pi. In fact, even A is also common. From here you have 1 by 1 and here you have 1 by 4. So 1 minus 1 by 4 is 3 by 4, right? So this will become 3 times mu naught I whole thing divided by 2 fours are 8, 8 pi A. That is the answer in the x direction. Is this clear, guys? X direction, the force is this much. Net force will be towards the left direction. This will be towards the left direction because this is strong, this is weak. That's the answer. Perfecto. Amazing. Yeah. Yes. Do I upload? These are all live classes, my dear. And all these are recent videos, this year's videos. Old videos are also there. They are also very good. Each video has its own purpose. Like very old classes, they are very, very small classes back in the day. Then you have roar series, which are marathon one shots, big one short classes, but marathon types. And these classes are again breaking those marathons into small parts, but a new refreshed version of questions, fresh set of concept. That is what we are doing. Okay. Right. Awesome. Okay. Do not forget that too. A lot of you forgot that too. So 2 into 4 will become 8. Okay. So it will not be 4 pi A, it will be 8 pi A. Okay. Die creator. Awesome. So that's how you solve these questions on current carrying wires and which are curved or loops or everything. You need to be very careful about those conditions over there. Now in this question, I have one thing to ask you. Tell me whether there will be any torque, on this. Because see, forces will be there. Yep. On this particular loop, yes, there is a force here, there is a force here, there is a force here, there is a force here. Yes, net force will be towards the left. But will there be any kind of torque? What do you think? Yes, 6 months is good enough. Yeah, definitely. I have made a plan August to January. Please check that plan. It's there in the channel. Yes, there will be no torque. There will be no torque because these two forces are in the same line. These two forces are in the same line. All forces are collinear. All the forces are collinear. Therefore, there will be no torque. So the torque will be zero. Very, very important. The torque will not be there. Shouldn't we multiply by 2a? What 2a? Yeah, 2a is there. So 2a into 4 is 8. 8a. So 8 pi a is there, not 4 pi a. That's why I put 8 pi a below. Okay. So there is no torque in this situation because all the forces are collinear. This is a very interesting concept. See, imagine one force is like this and the other force is like this. Then those forces cannot create torque. The torque in such a situation is zero. But imagine one force is here and other force is here. They are no longer collinear. There is some distance, some gap between them. So definitely there is going to be a torque in such a scenario. So there will be definitely a torque like this. So torque in such a scenario is not zero. Okay. Only when the forces are along the same line, it's like pulling this pen from both the sides, it will not rotate. But imagine pulling from here versus here. One force is along this line, one force is along this line. So now there is a torque. Okay. So that's what it means. Okay. All right. Now that brings me to the concept of torque on a coil carrying current. Okay. Torque on a coil carrying current. So say for example, you are being given a coil like this. Okay. And let's say this is the length, let's say this is the breadth, and let's say, there are magnetic fields which are piercing through that loop. Let's say the magnetic field is going like this. Okay. This is the magnetic field lines, okay, which are piercing through that particular loop. Now, this particular loop, it is at an angle and there might be some forces. And if you try to figure out the forces on this particular loop, you'll realize because the loop is not exactly perpendicular to the magnetic field, in this scenario, you will see a torque acting on the loop. And it's not that difficult to see. Let's try that out. So if you look at the side view of the same loop, the side view, if I see it from here, the length vector is here, okay, and the magnetic field lines are going like this, okay. So the loop is here like this. You can see the current in this part is going down, then it will go inside and it will go from behind and it will then again come towards you. Okay, so that is how it is. It will go from behind, again come towards you, go down and go inside and come like that. Okay, you're just seeing the side view, you're just seeing the front part of the or this side of the loop. Okay, clear? Now, if you do IL cross B on this particular part, observe the current is coming towards you, the magnetic field is on the top, length cross B, length is towards you, magnetic field is on the top, the force will come this particular way. The force is going to come like this. The force is going to come like this. Same thing if you do it over here. The current is going inside. Observe it carefully. The current over here is basically going inside. The current is basically going inside. Length cross B. Length is inside, field is up. So L cross B will make the force go like this. Will make the force go like this. So there is a force which goes like this over here in this plane. And there is a force which goes like this over here in this plane. They are two separated by some amount. On these two sides, if you calculate, one force will be like this and other force will be basically like this, but they will cancel out each other. They will end up cancelling out each other. So you don't have to worry because they will be collinear. Yes, they will just be collinear. They will end up cancelling. They will be collinear. Okay, you can see that these two forces will be cancelling out each other. So the only two forces which remain, which do not kind of cancel, but rather, I mean, force wise they cancel, torque wise they don't. Torque wise they are creating a torque because they are no longer collinear. This is along this line, this is along this line. So you can see that they are definitely not collinear. So definitely there is a torque which is created in this situation. There is a torque which is created in this particular situation. Is this absolutely clear? Okay. Sir, if F2 and F4 are not same, then there would be a torque. Yes, definitely there could have been a torque if F2, F4 would not be the same. That would be completely non-uniform. Not a problem, Pritija, always welcome. Previously, why you shouldn't mention the unit length in the denominator? I'm not really sure, Maha. Which question are you talking about? Okay. So as you can see over here, my dear kids, okay, these forces are definitely going to create a torque. We can figure out how much that torque is. It's not a big deal. But the idea is the value of the torque which comes out in such situations, there is a logic behind it. And the logic is through rotational motion, whenever the forces are not collinear, there is a force here, there is a force here. They are called couple forces. They are called couple forces. And the torque which exists is the distance between them, distance between them multiplied by any one force, any one force, any one force. So say for example, the distance between them is d, then the torque which acts on it is the distance between them, which is basically d multiplied by any one of the forces, like in this case it is F. So d into F is basically the torque. Okay, so d into F is basically the torque. Same thing you can do over here. You can again basically show this extension. You can see this is the distance between them. This is the distance between them. Let's say it is d. So the torque which will come out, it will be nothing but that distance multiplied by that particular F. That distance multiplied by that particular F. Now, how much is that distance d? We can calculate that. It is not a big deal. So if you pay attention closely, what happens is in this particular geometry, this side length is there. Okay. This force is coming from here like this. You are extending it further like that. From here, let's say I drop a perpendicular like this, which is in the direction of the magnetic field anyways. Then this length is basically L. This length is basically L. This thing over here is basically your D. This thing over here is basically your D. If I take this particular angle as theta, then you can clearly see that sine theta is d by L, opposite by hypotenuse. So d will be L times of sine theta. D will be nothing but L times of sine theta. Similarly, if you ask me how much is this force itself, the force itself, observe carefully, on this segment of the wire is current in that wire, length of that segment into the magnetic field. Current is I, length of that segment is B, and the magnetic field is capital B. Okay, so that force is IBB and the distance is L sine theta. So substitute that, you will get most of the stuff out here. Yep. So the torque will be nothing but L sine theta and the force is nothing but IBB. Now, there is a better way of writing it. I'll tell you how. I will write length into breadth together. Then I will put sine theta separately. I'll just put sine theta separately. And let me put the magnetic field separately. You might be wondering, why the hell did I do that? Length into breadth separately, sine theta as it is, and magnetic field separately. I'm just rearranging it, manipulating it. What is the purpose of this manipulation? You might be wondering. Torque is there. Sine theta is there. I can see magnetic field is a vector quantity. I can see sine theta is related to the cross product, but I don't have a vector yet, though torque is a vector. This length into breadth is nothing but the area of the coil. So I'll put this as area. Okay. Oh, sorry, I forgot that current. My bad. Let me just put that current also. So sorry. Current was also there. Yeah, current was also there. So length into breadth. Yes, sorry. Yeah. So this I into A is now called as the magnetic moment vector. So L into B is the area. Current into a vector, scalar into a vector is just a simple vector. Now I can treat this like a new vector equation where this is one vector cross producted with magnetic field, which is giving me the torque vector. So that way I get the formula of torque. Okay. So I call this entity as the magnetic moment. I call this entity current into area vector as the magnetic moment. You might be wondering at this point of time, sir, where is the direction of this magnetic moment and etc. Don't worry, I will tell you. So I will call the magnetic moment as a new quantity, magnetic moment of the loop as current into area. This is a vector quantity. This is a vector quantity. And the symbol for that, usually I will use capital M, magnetic moment. Unit will be, this is ampere, this is meter square. So ampere meter square will be the SI unit of magnetic moment. So therefore, I can then finally conclude over here. Let me just get rid of this. So I can write down the torque as, instead of current into area, I will write down magnetic moment. Sine theta will still exist. Magnetic field will still exist. So therefore, I can then write it down as magnetic moment cross producted. Yes, instead of sine theta, we are just replacing it with cross product with the magnetic field. So I don't need this anymore. So this is the formula for the torque on a loop. This is the formula for the torque on a loop in a field. Torque on a loop in a magnetic field. So this M is called as the magnetic moment. Symbol is M, ampere meter square. Ampere and meter square is the unit. How did I think of it? Because I saw that in this particular derivation, L and B and current are together. Sine theta is separate, magnetic field is separate, and torque is a vector. So I thought maybe now sine theta is coming, so there is a cross product. There is a vector here, there is a vector here. So deliberately, I generated a vector, I invented a new vector called magnetic moment. It did not come naturally. I defined it to be current into the area vector. Got it? I hope this is absolutely clear. Awesome. So what happens then? What happens then is we just need to see what is the direction of magnetic moment vector, which is the same as the area vector direction. If you remember Gauss law area vector, we have already done that. So the logic is exactly similar. So whenever you have a
surface, the area vector is always going to be perpendicular to it. So this is that surface of that loop. Imagine you dip it in a soapy film. So my area vector is just going to be like this. This is going to be the area vector, also the direction of magnetic moment. So magnetic moment area vector will be like this. Here also you can see it will be in this direction. This is the magnetic moment direction. If you notice, the magnetic field is over here. Magnetic field is over here, and the angle which we are talking about is theta, right over here. Yeah, that is the angle theta between magnetic moment and magnetic field. Okay, this is how it looks like. Everybody understood till this point? Awesome, awesome. Definitely, Nitin, we are here to support and motivate you. Please check out our strategy videos, whatever I have put the plans and everything. I've already put up how to improve your scores from mains to advanced, how to balance boards and JEE, what is the 99 percentile strategy, everything, online, offline coaching. We have created a podcast, all these things, and how to use AI for JEE. All these things are there for you. Please use these videos. Okay. Don't cover 50% of syllabus, you can cover more than that. And I have given a plan. Please follow that plan. August to December, January, what is that plan? What is given to you? Okay, Spidey? Awesome. Now that we are done with the magnetic moment, in general, what if the coil has n turns? So if a current loop has n number of turns, then the net magnetic moment will be, each coil will have I into A moment. So N times IA. So N times I will be the magnetic moment. NIA is the formula. NIA is the area vector, M is the magnetic moment, N is the turns, I is the current. All right. So with this, I think we can start solving some questions based on this. So we got NIA. All right. So say for example, question comes, a solenoid of 4 meters length has a cross section of 2 centimeters square and 100 turns per meter. Find the magnetic dipole moment or magnetic moment of that particular solenoid. Find the magnetic moment of that particular solenoid. So see guys, when you have a solenoid, there are many turns in that particular solenoid. Each coil will create its own magnetic moment. All these coils together will create the net magnetic moment. So the magnetic moment of the solenoid will be magnetic moment of any one coil multiplied by the number of total turns which you get. Okay. Now, what is the total number of turns? Well, 100 turns are there per meter. So, if there are 100 turns for every 1 meter, therefore, for 4 meters, because it is clearly mentioned the length of the solenoid is 4 meters, how many turns will be there? Can you guess how many turns will be there? Obviously, 400 turns will be there. So there are 400 turns over here, and each turn has a magnetic moment. And what is the magnetic moment formula? The magnetic moment formula is NIA. NIA. Well, for a coil, number of turns is 1. Current, I think, needs to be given. Maybe it was not given. Let's say the current is 0.1 ampere. Chumma I'm taking. So let's say the current is 0.1 ampere and area of cross section 2 centimeter square. So 2 centimeter is minus 2, square means minus 4. That's it. So this is what it should look like. 400 into n is 1. I is 0.1, area is 2. Current, if it is not given, then we cannot solve the problem. So current needs to be given. Let's say it is 0.1 ampere. Let's assume it. Okay. So now can we solve this and see how much is the answer coming out to be? 400 into 2 will become 800, and 0.1 and 10 to the power minus 4 will make it minus 5. So it will become 8 into 10 to the power minus 3. So that much ampere meter square is the magnetic moment of the solenoid. Okay, 8 into 10 to the power minus 3. Is that okay? Clear? That's how you solve this question. Awesome. Let's do the next question coming up on your screen. There are two concentric loops, radius R1 and R2, placed in the xy plane. Current of 7 ampere is flowing through them in the direction as shown. The net magnetic moment of the system is how much? Notice how current is going this way and current is going this way in two different coils. So each one of them will produce different moments. Like for example, this current in this particular loop, if the current is going like this, the direction of the magnetic moment, if you curl the fingers, wherever the thumb goes is the direction of magnetic moment. I think while explaining over here, I missed that particular point. What is the direction? So always, whichever direction the current is flowing, if you take that particular direction, like in this case, like this, for example, over here, if you take like this in this example, if you curl the fingers in the direction of the current, the thumb points in the direction of the magnetic moment. So curl the fingers of your right hand in the direction of the current. The right hand thumb will point in the direction of the magnetic moment. That is the simple right hand thumb rule. So over here, just if you notice, when the current is going clockwise, the magnetic moment is definitely going inside. The magnetic moment is definitely going inside. For the other one, when the current is going like this, curl the fingers this way, the thumb comes towards you, so the magnetic moment is towards you. Both are opposite in direction but also different in magnitude. How much will this guy's magnitude be? There is only one turn, so n is 1. Current is how much? I think it is given to be 7, and area, which is pi into r square. R for the bigger one is 50 centimeter, so it is basically 0.5 square. So pi is basically 22 by 7. 0.5 means half square is 1 by 4, 7 cancels. So 22 by 4, which is 11 by 2. 11 by 2 ampere meter square is this guy. M2 will be number of turns into current into area, which is pi into r square. R is 0.3, so 0.3 square. So again, 7 into 22 by 7. 0.3 square means 0.09, which is 9 by 100 basically. 7 cancels. Is that right? Perfect. Over here, 7 cancels, and 22 into 9. How much is it? 198. Yeah, 198, because if you add more 22 to it, you will get 220. 198 divided by 100, which is 1.98 ampere meter square. 11 by 2 means how much? It is basically 5.5 ampere meter square. So M1 is this much, M2 is this much. You just have to take the subtraction of these two. That will give you the net magnetic moment. So the net magnetic moment will be M1 minus M2, whichever is bigger, whichever is smaller. Obviously, M1 is bigger than M2. So you will have 5.5 minus 1.98. How much will it be? 1.98 is close to 2. So it will be 3 point, close enough to 3.5 approximately ampere meter square, which is 7 by 2 ampere meter square. Close enough to 7 by 2. Now, which direction will it be? It will be inside, right? It will be inside. Yeah, it will be inside because the bigger one is this. This is the smaller one. So inside is which direction? I think negative k by 2. Yeah, negative 7 by 2 k cap. That is the answer, which is B option. So B option is the correct one. Very simple. Yes. B. B is the right answer. Yeah. Amazing. Moving to the next question. Yes, B was the correct answer, as you can see over here. Next question coming up on your screen. The question says the dipole moment of a loop is I. M is the magnetic moment of a current loop I is M, and the magnetic field at the center is B1. When the dipole moment is doubled, keeping the current constant, the magnetic field at the center of the loop is B2. What is the ratio? Beautiful question, guys. Beautiful question. Just observe carefully. This is that current carrying loop. Okay. Because of that current, what happens is there is a magnetic moment which is created. Let's say we call it as M. And because of the current, do not forget there is also magnetic field at the center, which you have studied in the previous chapter. Oh, both their relationships are being compared now. Let's understand it one by one. What is the formula for magnetic moment? The formula for magnetic moment is number of turns into the current into the area. Okay. Number of turns is 1, so forget it. Area is pi r square. So this is magnetic moment. Great. What about magnetic field formula? The magnetic field formula is mu naught current divided by 2 times of r. Somehow, let's get rid of r and let's get it in terms of m. That will make it easier. So I have an idea over here. Let's write down what is r square. R square will be m by I pi. Therefore, r will be root of m divided by I pi. So why I need this? Because when I write magnetic field, which is mu naught current divided by 2 times of r, mu naught is there, current is there, 2 is there. Instead of r, I will put this. So instead of r, I'm just going to put this. But m is downstairs and I pi is upstairs. Okay. So what happens next? Oops. Magnetic field. Therefore, magnetic field. This is a constant, this is a constant, this is a constant, this is a constant, this is a constant. It is basically inversely proportional to root of magnetic moment. Can you see that? It is directly inversely proportional to the magnetic moment's root, because everything else is a constant. So now, when this relationship is obtained, doing this concept is very easy. B1 by B2 will be root of M2 by M1. Root of M2 by M1. Magnetic moment, it is mentioned, the magnetic moment is doubled. So M2 is the double of M1. So therefore, B1 by B2 will be root 2 is to 1. So root 2 is to 1 means C option is the right answer. C for Captain Shreyas. Amazing. No, magnetic properties and matter is not required for this chapter. It's a separate independent thing. After that, uh, after this, doing that chapter will be easy, because here we introduce the concept of magnetic moment at chapter. Yeah, very nice question, guys. And moving on then to the next question, killer question, which was asking JEE 2019. Observe. A square loop is carrying a steady current and the magnetic moment is M. Square loop. If the loop is now made into circle, what is the new moment of the circle? Wow. What are we really doing over here? We had a square loop and we are converting it into a circle. Okay. So in this process, what might exactly change which changes the magnetic moment? Let's understand. See, we know magnetic moment is number of turns into current into area. This is anyways 1. This is anyways same. Oh, the area definitely has changed. Maybe that is the reason. So the magnetic moment of the circle upon magnetic moment of the square, if I divide them, n is same, I is same, area of the circle by area of the square. Area of the circle is pi r square. Area of the square is side square. So maybe I just need to find the relationship between the radius and the side of the square. Then my job is done. So the side length is a and the radius is r. In this process, do not forget that the perimeter is same. Reason, because the wire length is going to be the same. Oh, so what is the perimeter of this guy? It is nothing but a plus a plus a 4 times. So it will become 4a, and perimeter of this is 2 pi r. Okay, 2 cancel. So 2a is equal to pi r. Therefore, r is equal to 2a divided by pi. Oh, nice. So if I get r is 2a by pi, why not put it over here? So squaring r, it will become 4a square by pi square. Okay, 4a square by pi square. This pi is there. This a square is also there. I just squared r. R square will be 4a square by pi square. Pi goes off, a square goes off. So what am I really left with? 4 divided by a pi. 4 divided by a pi, that is magnetic moment of circle by magnetic moment of the square. Magnetic moment of the square is m. Yes, the square loop has a magnetic moment m, that is given. So magnetic moment of the circle will be 4m. Sorry, a got cancelled. No, why did I put it here? So sorry guys. 4 divided by pi. 4m divided by pi. That's it. That is the answer. 4m divided by pi, which is D option. Perfect. Amazing. Amazing. What a brilliant, brilliant question. Really, a square had got cancelled. Okay. And here also one of the pi got cancelled. Only one pi was remaining, 4 was remaining. This square magnetic moment was m. Nice. So perimeter was constant. So different concepts can be mixed. Geometry, anything can be mixed, and you can get the questions done. Really loving it. I hope you are liking the session. If you are not yet subscribed, please subscribe to the channel. Yeah, very, very important. Okay, interesting question coming up ahead. Find the magnetic moment of the current carrying loop A, B, C, D, E, F, A. Each of the loop is 10 centimeter long and current of the loop is 2 ampere. Each side of the loop is 10 centimeter long. Okay. 10 centimeter, everything is 10. Okay. Let's do this. Whenever you see such questions, I'll tell you what, there is a simple trick for solving them. And the trick is, see, imagine this particular currents which are going like this. Imagine I show it like this. One loop here. Imagine the current is going like this. And another loop over here. Where current is going like this. Can I tell that this loop, which is in two-dimensional plane, or sorry, two planes rather, it's in 3D. It's like a loop which has been bent like this in two planes, is a combination of these two loops. Like, sir, wait a minute. In this loop, the current is going like this. In this loop, the current is going like this. Won't it cause any problem? I say no. Say this part, this part, this part, this part, this part, this part, everything is same. The only part which is common, which is this, there also the currents are getting cancelled. Observe carefully. Here, the currents, the net current is basically zero. One current is going like this, the other current is going like this. So strictly speaking, this is as good as not there. So if you forget that, you get your original loop. You get your original, loop over there. Wow, sir, this is so cool. What to do now? See, man, it's very straightforward after this. For this particular loop, the current is going like this. The magnetic moment will be down. The magnetic moment will be downwards like this. So this is the magnetic moment of this loop. Let's say I call it M1. For this loop, current is going like that. The magnetic moment is going to be there somewhere like this. The magnetic moment is going to be there, M2, let's say. If you look at it from this side, M2 is over here, M2 is over here, and your M1 is like this. Best part, both M1 and M2, magnitude wise, M1 and M2 magnitude wise are exactly going to be the same because same dimensions, same current, everything. It will just be NIA formula. Just use NIA. Number of turns 1, current, 2 amperes. Area side square, which is 0.1 meter into 0.1. So how much will it be? 0.1 into 0.1. So that will be 0.02 ampere meter square. That is each magnetic moment. But we have to find the net magnetic moment. So net means it will be the vector sum. So this will be the net magnetic moment. What will it be? It will be just m1 square plus m2 square. So each one of them is same only. So it will be m1 root 2 because both are same. So m1 is nothing but 0.02 and into root 2 ampere meter square. So that is our net magnetic moment. It is at an angle now. It is at an angle. All right. Amazing. Did you love this question? How we dissected the question into two parts. Whenever you find these bent loops, right, they are usually the combination of two separate loops. These kind of questions are again very common in your PYQs also. Okay, standard model of questions. Very nice. Now let's see what is the magnetic moment of a rotating body, revolving body. That's the last concept which we have for today. Okay, that's the last concept. You'll be like, what? Magnetic moment of a revolving body? I'm not able to understand. What the hell is this? Hold on. Say we have a charge which is rotating. If the charge is rotating or revolving, a revolving or rotating charge, won't it act as if a charge is moving in a path, a circular path? Okay, so it is like motion of charges in a closed path, and what does it behave like? Charge is moving like this, round and round and round and round like this. It behaves like a current carrying loop. It behaves like a current carrying loop. Oh wow, perfect. If it is a current carrying loop, what does it create? It behaves like a magnet. Yes, it behaves like a electromagnet because it's because of electricity, current electricity. So that's why it behaves like a electromagnet. And whenever you have a magnet, it has magnetic moment. So it definitely has magnetic moment associated with it. Is this logic clear? Why rotating charges, revolving charges generate its own magnetic nature? Just imagine an electron revolving in an orbit behaves like a magnet. So that is how the magnetic properties come in the first place, which is the basis of the next chapter. Yeah, amazing. Thank you, Siva Karthik. I'm so glad you are at Amrita Vishwa Vidyapitam. And with computer science, I mean, we made so many videos of Amrita this year actually. and I'm pretty sure it would have benefited you. I'm proud of you, my dear. All the best, and so glad that you guys come back. And this is the beauty of this channel, that almost every student who graduates from this channel comes back, puts a comment, tags us on Instagram, or just puts up a live chat, notice, and guides and mentors our juniors. I'm so glad you guys keep doing that, and proud of all of you guys. Yeah. Physics problems are problems. I cannot solve mechanics. Please guide me for JEE Advanced. I would say, HV, if physics problems are problems, first start with, HC Verma, basic questions of DC Pandey or Tattva module. Very laddu questions. Understand the derivations. Go through my lectures, already done mechanics in multiple ways. Choose the easiest format, whichever is convenient for you, and then go to mains PYQs, and then go to advanced normal questions, then go to mixed concept questions, mixed pattern questions, and then advanced PYQs. Don't just directly jump to advanced. Yeah. Oh, welcome, Komla. I'm so glad you guys are here. Class 9th. You guys are in for a big surprise very soon. So the question now arises, what the hell is the magnetic moment of this guy? Okay, can we find the magnetic moment? Why not? But for that, we need to find the current first, and then we can do the rest. First, let's find out the current. The current, equivalent current, is how much charge which flows upon the time period. As you can see, the charge which flows is Q, time period is T, and time period, I can always put it as 2 pi divided by omega. So it will become Q omega divided by 2 pi. Now talking about the magnetic moment, number of turns into current into area. Number of turns is 1, current is what I just got right from there, which is Q omega divided by 2 pi, omega being the angular speed. Area is basically pi r square. So therefore, the magnetic moment, pi cancels, will become Q omega r square divided by 2. Perfect. So we got this. Do I need to remember it? I would say no, not yet. Don't remember it. Why, sir, not to remember it? Hold on, I'll tell you why. Now let's say whatever magnetic moment we got, I'm not really quite happy with it yet. I try to figure out one more interesting thing. What's that interesting thing, sir? Let me find the angular momentum. I was like, what? Angular momentum, sir? Rotational chapter. If you have done it, it will be easy, else slightly difficult. Angular momentum is mass into radius into velocity. Here, the velocity itself is omega r, circular motion concept. So it will become m omega r square. That is the angular momentum. Okay, so the angular momentum is m omega r square, which is also moment of inertia into omega, one and the same thing. Now, sir, I have an idea. Let's take the division of magnetic moment, which is q omega r square by 2, divide it with angular momentum, which itself is m omega r square. M omega r square. That's it. See, what do we exactly get? So magnetic moment divided by angular momentum. What really are we getting? Omega just got cancelled. R square got cancelled. We are just getting Q by 2m. Yes, are we just getting charge? What is that? Charge divided by 2 times the mass. Charge divided by 2 times the mass. That's it. That is the answer that we are getting, which means this is not just a coincidence. It will happen every single time, whether you take a charge, whether you take a big charge, whether you take a ring, whether you take a rod, whether you take a disc, sphere, anything. As long as you're rotating, the ratio of the magnetic moment and angular momentum will be the charge which is being rotated by 2 times the mass. This special ratio is called as the gyromagnetic ratio. Gyro is related to rotation. So this is gyro, this is magnetic. So gyromagnetic ratio. Gyromagnetic ratio of rotating bodies. Angular momentum can be easily found. taking charge and mass, you can easily find the magnetic moment. So that saves me the headache of this procedure where you find the current separately, then you find the magnetic moment. Headache, big headache this is. Directly we can get through the gyromagnetic ratio. This is not just true for a point charge, it is always true for any rigid body. For any charged rotating body, for any charged rotating rigid body. Okay, so very important. Gyromagnetic ratio. Gyromagnetic ratio. Let's see the applications of it one by one. Okay, I have put up the result already over here, but still I will make you solve few problems. Say for example, there is a rod which is hinged at one end and it is rotating like this. Can we find the magnetic moment? Yes, why not? First, let's find the angular momentum, which is I into omega. Moment of inertia of a rod is ml square by 3, not 12, at the end into omega. That's it. Now let's use gyromagnetic ratio formula. M by L is the total charge by 2 times of mass. So magnetic moment is charge by 2 times of mass and angular momentum. Whatever was this angular momentum? What was that angular momentum? ml square omega divided by 3. Perfect. So we'll get the answer. Magnetic moment will be cancels. It will become q omega L square by 3 to the 6. Q omega L square by 6. That is the answer. Q omega L square by 6. Perfect. That's it. Very easy to solve. Don't have to by heart. Just know the angular momentum formula and use the gyromagnetic ratio formula. That's it. Done. Dusted. Is that clear? Yep. Everyone? Okay. I hope this is absolutely clear. Very nice, very nice, very nice. Perfect. Now let's see some other question over here. Let's say we have a charged ring. Can we do that also? Why not? Again, what is the angular momentum if this ring begins to rotate? Use I omega. Moment of inertia is mr square, so into omega. Now use gyromagnetic ratio. M by L is charge divided by 2m. So Q by 2m will be as it is. Q by 2m will be as it is. Remember, there was L here. So L will go on the top. L when goes on the top, it will become m r square into omega. That will be your magnetic moment. So magnetic moment will be cancels. So Q omega r square divided by 2. Perfect. Done. Dusted. Simple, right? So any charge rotating body, it will uh, easily be calculatable. Thank you, Abhiram. I'm so glad you are loving the Eklavya batch. Already the lectures have started in the Eklavya batch. If you have not joined yet, other students, please consider joining it as soon as possible. Same thing for a disk, guys. Do it. Angular momentum of a disk, I omega. Moment of inertia, mr square by 2. Okay, mr square by 2. So magnetic moment by angular momentum is q by 2m. So therefore, what will be the magnetic moment? So here we had L. So L goes on the top. It will become mr square by 2 into omega. And the rest of the terms, which is q by 2m, will stay as it is. So therefore, magnetic moment will be cancels. Yeah, will become q omega r square 2 to the 4. Q omega r square by 4. That is exactly the answer. Same thing for the ring over here. So nice. Now I want you to try out for the hollow sphere, okay, on your own, and also charged solid sphere uniform. Both of them I have put the solution, but just try it on your own. You will see that it is very easy to find it out. Okay, so now any kind of body you can easily do it. So today we have learned amazing stuff. Started off with how Lorentz force gets converted to a force on a current carrying wire, then curved wires, then loops, then force on a loop, then force between the wires, torque on a loop, magnetic moment, and then rotating charges and its magnetic moment. Okay, so all of this was covered today. So beautiful class, wonderful class in detail from the scratch with some derivations as well. So hope you liked it. I mean, literally like the video also, and subscribe to the channel, else you will miss out on all the live classes daily which are happening at 8 o'clock and 6 o'clock. Okay. So this is the #1 JEE English channel, guys. Spread the word. Keep watching, because this is the only channel which will give you quality content. If you are a student from South, especially, this is a boon for you, because again, you will miss out on the JEE level stuff, or else you will just remain at the local CET level. You will not be, at par with the JEE level. So make sure you are subscribed on the JEE channel and watch every single class right over here. Thank you so much. See you. Hasta la vista. Signing off.